Hello, my party people. We are going to do a lecture on exercise physiology this time. So we had the tutorial video a little bit earlier on the channel about exercise and the heart, specifics with that. Now we're going to just go through the whole exercise physiology spiel. So talking about exercise as it relates to the body and what happens with changes there. So exercise physiology, right? As it would imply, is the study of the mechanisms that are going to be happening during and after physical exercise. So this is going to consist of the training portion, as well as the body's adaptations to it and what happens as far as recovery in the immediate periods after exercise. So first we have to categorize what exercise is, and in relation to body, that means its metabolic needs, right? So the metabolic needs of exercise are going to be what we classify as the exercise intensity. So mild exercise is going to be variable, anything up to 450 calories, all right, per hour. Heavy is going to be 450 to 600. Super heavy is going to be over 600 calories per hour. Okay. Now this can be achieved in a variety of ways. This is simply a caloric definition. This doesn't have to do with anaerobic or aerobic intensities or modes of cardiovascular exercise, things of that nature. We're going to characterize oxygen consumption as well. And really, to get the exact amount of intensity per calorie measurement, we need to get the oxygen consumption, because the oxygen rate of respiration, the amount of oxygen breathed in versus breathed out, carbon dioxide, is going to give us an exact calculation of the calorie expenditure during that time. So oxygen consumption during normality or during rest is usually around 250 milliliters per minute. If we go up to maximal exercise, maximal intake could be around the realm of 3 liters per minute. So pretty massive increase there as far as exercise intensity and oxygen consumption. Oxygen consumption is going to be measured in VO2, which is going to be the volume of oxygen in a certain period of time. VO2 is going to be the volume of oxygen that we can physically get in. VO2 maximum is the maximum percentage of oxygen that we can get in. So we're going to be relating this to a subjective level because this is individualized. So it's the amount of oxygen that any one person individually can take in. Mild exercise, maximal oxygen consumption being what it is, you're going to be at about 33% or a third of this. Moderate, 50%. Heavy gets up to around 70. Anything above 70 is going to be super heavy exercise. Looking at oxygen deprivation, all right, we look at something like a pulse oxygen percentage, which is going to be the volume of oxygen that's transported by one pulse or one stroke of the heart. If we look at consumption and intake of oxygen at rest, again, about 250 milliliters. So if that's the case, then we know that resting heart rate is going to be around 70. If we take that calculation, that means that we're going to have, during exercise, we're about up 20 milliliters of oxygen per pulse of blood. All right. So our first mechanism of regulation is going to be neuronal. The neuronal regulation is going to come from two mechanisms. It's going to come from the autonomic nervous system. It's going to be the sympathetic and parasympathetic sides. All right. So the autonomic nervous system changes. All right. First, we're going to reduce parasympathetic tone. Parasympathetic tone is what gives us our resting heart rate. It's what keeps that heart rate depressed during resting periods. So during our first phase of exercise, parasympathetic tone is going to be reduced. Second phase, and with any sort of prolonged activity or prolonged exercise, is going to be basically sympathetic induced activation. And this is going to kick up the heart rate and increase the sinoatrial node depolarization time frame. The humoral regulation is going to be the hormonal side of things. All right, here we see the adrenal medulla, which is going to release our catecholamines, epinephrine and norepinephrine. These are both going to have chronic prolonged effects on the heart as far as increasing heart rate and stroke volume, and also on the liver to increase the mobilization of glycogen stores and free fatty acids. As far as the hypothalamus is concerned, we have the hypophysis between the anterior pituitary and the hypothalamus. The anterior pituitary signaling is going to increase, and we're going to increase in hormonal production of growth hormone. Growth hormone is going to stimulate anabolism, which is a building process, right? Strengthening of all muscles, ligaments, tendons, things like that. In the adrenal cortex, we're going to release glucocorticoids, mostly cortisol, right? This is going to rise during heavy and prolonged exercise. This is going to cause a lot of blood glucose to be alleviated from the bloodstream and taken into tissues. So we're going to see hyperglycemia, mobilizing fat and proteins as well. Next is prolactin. Prolactin is going to, again, come from the hypophyseal portal system with the pituitary gland. Release of this is going to increase the blood levels, right? We're going to increase mobilization of fat, and it also has an antidiuretic effect on the kidneys. We also have endorphins. These are going to be released, right? This is going to have a similar effect to opiates, and opiate medications are going to stimulate receptors that normal endorphins would. So this is pretty much going to be just like taking an opiate in a very acute setting. Increase this during endurance exercise, right? The psychological effects causes the depression of fatigue, right? Can also increase euphoria. Together with prolactin, is responsible for exercise-induced amenorrhea, or lack of a menstrual cycle in the female. For the pancreas, we see that the insulin secretion and production is going to go down, right? So it's going to drop by about 50%. Decrease in the insulin secretion plus the increased uptake of the hormone by muscles during this time is going to lead to a large drop in the bloodstream levels. Hypoglycemic effect combined with the higher consumption of glucose afterwards. Okay, glucagon levels are going to go up. Glucagon levels will rise, and that is going to enhance the mobilization of the liver to promote glycogenolysis, which is the cleavage of glycogen into glucose. So for exercise and heart, we had the tutorial video on this. I will go over it very mildly here. Okay, so the heart is going to have a rapid onset increase of heart rate. This is going to be a reduction of the vagus nerve, which is our parasympathetic input here. Calculating heart rate training zones, right? You're going to take your heart rate, which is going to be a general calculation of 220 minus your age, right? Or if we want to do the mathematical, we can do 217 minus 0.85 times your age. Both of them are going to yield somewhat similar numbers. The calculation, but the multiplying is going to be a little bit more accurate. All right. Heart rate changes in recovery phase. During the first minute, we're going to have an immediate exponential decrease in heart rate. During the second minute, we're going to reactivate the vagal nerves and the parasympathetic tone. So it takes a couple of minutes to get that to reactivate. Progression is going to cause reduction of sympathetic and hormonal activities. Stroke volume and cardiac output. Stroke volume is going to increase by about 20 to 30% at roughly 50% of the maximum oxygen uptake, or 50% of your VO2 max. This is going to be followed by a steady state. So at that time, after we get to that point, the increase in blood flow is going to be reflective of heart rate. So cardiac output is going to go up, and the intensity of your exercise, if it continues to rise, will cause cardiac output to continue to rise. That will be a reflection of the heart rate increasing. So once the stroke volume has steadied off, right, after we get to about 40% of the VO2 max, then heart rate is responsible for the increase in cardiac output. All right, cardiac output is going to be a product of the heart rate and the stroke volume. At rest, it's going to be anywhere from 3 to 3.5 liters per minute. maximum cardiac output, we can get it up to close to 20 liters per minute, in women, and up to 25 in men potentially. And then we see for long range endurance athletes, especially pro level, Olympic level trained athletes, it can get into the range of 30 to even 35 liters per minute of output. Blood pressure, this is going to be both systolic and diastolic, right? Systolic is going to be blood, the pressure on the vessels during contraction. Diastolic is the pressure on the vessels during relaxation of the heart. For systemic blood pressure, the systolic is going to rise pretty sharply during isometric and sustained rhythmic exercise. This is going to get up to around 200 millimeters of mercury, which we know is a good 80 above what the average should be. Diastolic is going to stay relatively similar. So the diastolic is going to remain somewhat close to what its resting value is. It's going to be influenced mainly by the peripheral vascular resistance. So if there's vasodilation in the skeletal muscles during circulation, that really will go a long way in reducing the pressure on the vasculature during diastole. So we don't see that big of an increase in the diastolic number. For pulmonary blood pressure, it's going to increase a little bit, right? During isometric exercise or stretching, it could go down or up. If we have impairment of venous return and the venous system is not working well, this will cause an increase in venous pressure. So we could see an increase in the diastolic number for the pulmonary system if the venous response is not adequately approaching it. So the distribution of blood flow, we're going to see a redistribution of flow to the skeletal muscle during work, right? Usually at rest, we're going to get about 200 capillaries or so open in working in skeletal muscle per millimeter squared. In working muscle, however, we can open this up to 2,000, 3,000 capillaries per millimeter squared. So blood flow could increase a good 10 to 15 times above average. So instead of getting 2 to 5 milliliters per minute per 100 grams of muscle tissue, we can go up to 120. Okay, let's see. The number of hormonal regulation. So for the blood flow to other organs, what we see is a very sharp decrease in blood flow to the splanchnic organs, which is going to be your visceral organs. The redistribution of that is going to go to the blood and skeletal muscles. Right? So the visceral visceral blood flow is going to drop to only about 30% of whatever its resting value is. The brain, however, is going to really keep its blood flow pretty much constant. The only difference is that the blood flow is going to be diverted or redirected to the areas that are causing aid to the exercise, such as the motor cortex, visual cortex, things like that. So we get a relatively constant blood flow to the brain. However, during activity, the blood flow is redistributed to wherever it needs to go as far as the areas of the brain that are most in tune with the activity that you're doing. All right, during exercise, especially prolonged exercise, endurance exercise, we see an increase in viscosity in the blood because we have an increase in red blood cell concentrations, which leads to a higher hematocrit, right? We can see increase in filtration pressure at the capillaries of the skeletal muscle and higher production of red blood cells. Leukocytosis is going to be increase in white blood cells. We're going to see this because of demarginization. We see mainly neutrophils and lymphocytes increase. For the blood plasma, all right, for short-lasting exercise, we can see an increase in the glucose levels, so we see hyperglycemia. During long-lasting or endurance training, there will be a net overall drop in glucose level, so this would be a hypoglycemic state. Lactate levels are going to rise slightly. It depends on the mode of exercise that you're doing, but mostly we see that we're going to have an increase, all right? If we have a exercise session in the last 15 minutes, we can see up to a 15-fold rise in blood lactate levels Um, so for heavy exercise over time, we're going to see that increase. Moving on to the respiratory system and ventilation. Ventilation is going to be a product of respiration, right? So breathing, of course, during exercise, oxygen requirements are going to go up. During mild exercise, we're going to rise as far as the respiratory rate proportionally to the oxygen intake or consumption that's needed. During heavy exercise or really intense exertion, ventilation is actually going to be over proportional, right? So this is going to be an additive stimulus. Potentially, we could be responding to metabolic acidosis, which is going to be an increase in lactic acid in the bloodstream, and this is going to be sensed by central chemoreceptors. Ventilation, interestingly, is not the maximal effort regulator, so it's not a limiting factor for reaching maximal effort. Ventilation at about 80% of the maximal value is going to cover the need of maximum effort. So really ventilatory oxygen consumption in a normal non-diseased person should be adequate to reach maximal effort and efficiency. So our maximum aerobic capacity, right here we're talking about the oxygen consumption that we can get in a maximal respiration cycle. If we increase the load of exercise that we are doing, we're going to see a linear rise in oxygen consumption. Right? If we have a disproportional rise between the requirements and the intake, then it's going to lead to exhaustion and fatigue. Once we reach a plateau, that means that the maximum oxygen uptake or consumption is going to equal the maximum aerobic capacity. And this is going to lead to what we term oxygen debt. Right? Now, oxygen debt, as we define, is going to be the ATP in working muscles not able to be kept pace with their utilization. So that means that the anaerobic pathway is going to be limiting. Oxygen debt will occur, and that means that the period after exercise is over, you're going to have an extra need of oxygen that's going to need to be consumed. So we have to take in extra oxygen after the exercise period is done in order to assist in removing things like lactate, replenishing ATP and creatine phosphate, and replacing oxygen that has come from the myoglobin stores. Oxygen debt is going to be measured by determining the oxygen consumption after exercise until we have a constant basal consumption of oxygen, and that depends on how long it's going to take to get there. After mild exercise, oxygen debt could be about 4 liters. After a very heavy, intense session, it could be up to 20 liters of oxygen that is needed. For blood gas values, here we see the partial pressures of gases. After mild exercise, blood values are not going to be terribly different, but during heavy exercise, after we're finished, we can have a decrease in the partial pressure of oxygen by about 8%. We'll also see a drop in the partial pressure of carbon dioxide, right, by about 10% or so, and this is due to hyperventilation during heavy exercise. So acid-base balance is a big constituent for exercise. Again, we have to get this oxygen carbon dioxide balance under control, and that is going to be a lot of what the acid-base balance is. So for heavy exercise, we see metabolic acidosis because of compensated hypocapnia, right? This is the tendency for respiratory alkalosis during this time, or overventilation, breathing out more carbon dioxide than needed. Looking at metabolic specifics, right? For the metabolism of the skeletal muscle, for our very short periods, we're going to use anaerobic pathways. So for things like up to 20 seconds of activity, we can have utilization of ATP from the creatine phosphate storage and the creatine phosphate metabolism system. Exercise duration that is going to last up to 6 minutes, right? We can see a switch off in this time period. So for the first minute, we have anaerobic glycolysis, lactate accumulation. Anaerobic glycolysis is a maximum of about 45 seconds or so. Aerobic metabolism is going to pick up after about 2 minutes into exercise. For endurance performances, we see that aerobic metabolism is going to be our glycogen stores plus oxygen. And this is the time of the exercise limited mainly by exhausting glycogen storage. All right, so for thermoregulation, we're going to see an increase in heat and increase in central temperature simply because the muscles are contracting and producing heat. Now, if it's a very warm environment, hot environment, intense exercise, sweating rate can be up to a liter or so per hour. Long-lasting sweating is going to cause fatigue of sweating glands. So that means that you are arresting the sweat production less evaporation method, and that can lead to hypothermia. If we're doing heavy muscular work in a hot environment, you're going to redistribute a lot of blood flow to the skin circulation. So we're going to see limited skeletal muscle perfusion and physical output because of the fact that the redistribution of blood flow is so severe to the skin surface to decrease body temperature. So here's a couple of effects of training on physiological parameters. Training is going to be defined as regular exercise or repetition of sport activities. So for a blood volume, right, normal blood volume is going to be about 5 to 6 liters or so in a non-trained person. After training, we could have up to 9 liters of blood if necessary. Right? Heart rate, again, this is going to be a little bit on the extreme end, but without training, someone's resting heart rate could be around 80. After training, we could get down, maybe not to 40, but maybe 60 or 50. Heart rate maximum isn't really going to change. Right? We're not going to see much of a difference there. Your heart rate maximum is going to pretty much be consistent with what your age is. Stroke volume at rest is going to be increased because of increased contractile efficiency. So our stroke volume at rest can be up to 140 milliliters in a trained person. Maximal stroke volume also going to increase, and this is where we see a lot of the increase as far as cardiac output goes in exercise. Cardiac output at rest is going to be relatively similar. Cardiac output maximum, because of that increased stroke volume, is going to be very high. So we can get it up to 10, 12, 15 liters more than an untrained person. Heart weight is going to increase because of increased musculature and contractile strength. Ventilation, respiratory exchange is going to be more efficient, and we can increase the amount of oxygen that we take in almost twofold, which we can see from our maximum oxygen consumption. All right, so a couple of different adaptations here that we can look at. First is going to be bradycardia in subjects under endurance training. That means that someone with a large degree of endurance training or has done a lot of endurance training in their lives can have a low heart rate or bradycardia at rest. Mechanisms here is predominancy of vagal tone. So this is going to be a dynamic shift of autonomic nervous system impulses towards the parasympathetic side. We see a reduction in the intrinsic heart rate of the sinoatrial node because of this. So our rate of spontaneous depolarization is going to be less. We see a reduction of beta adrenergic receptors in the right atrium, change in compliance, and morphological adaptations. Morphological adaptation is referring to the physical changes. So the actual hypertrophy of the myocardium, dilation of the heart cavities. We see hypertrophy in the walls of the heart, especially in the left ventricle because of systemic pumping of that blood. This is also reflected in an ECG where we see an increase in the curvature over the LV or V3 to V5 leads. Effects of training on the respiratory system, increasing capacities. All right, so our ventilatory reserve can rise from 1 to 5 to 7 to 9 to 15 liters or so, as far as that is concerned. We see longer apneic pauses or longer voluntary apneic pauses. That means longer periods where we don't have to breathe and we just don't breathe voluntarily. Increase in maximum oxygen uptake or consumption. Again, we can get a double of this. We can doubling from 3 to 7 liters per minute. For the bone, this is going to be a product mostly of what kind of exercise you're doing. So resistance exercise is going to cause more remodeling and greater bone strength and density, whereas endurance exercise, to a degree, can do the same unless it's way overdone. So for someone who's running 40 miles a day or something like that, you're going to have a net breakdown of bone instead, because that's going to cause too much strain, too much repetitive motion on those bones. For fatigue, fatigue is going to be a large limiter of performance. Of course, over time, your body's mechanisms are going to degrade as far as their ability to perform. So limitations as far as peripheral go are going to be musculature, the exhaustion of metabolic reserves like glycogen, accumulation of metabolites like lactic acid. These are going to cause less efficiency of muscular contraction. We also see psychological or central nervous system components. This is going to be a protective mechanism or a subjective feeling. We also are going to have central nervous system exhaustion. All right, so there's going to be slower signal transmission. You have inhibition of thinking and decision processes and emotional ability. So physiological is going to look at things like heart rate, all right? Pathological, this is going to be non-normal or some disease sort of processes like spasms, tremors, hyperemic skin, nausea, headaches, hypotension, cyanosis, things like that. Reactioning to non-physical forms of loading. This is referring to psychological and emotional loads. So reactions are going to be similar to physical exercise effects. So that means mentality changes or psychological detriment is going to be similar to physical exercise effects, where we see things like increased heart rate, ventilation, sweating, hyperperfusion of the cutaneous membrane with blood, sympathoadrenal system activation. And we're going to see this without increased consumption of oxygen, meaning that we have a stress system that is activated without any actual physical need for it. All right, so let's look at the physiology of musculature. Number one is skeletal muscle. Skeletal muscle, the fibers are about 10 to 80 microns in diameter. These extrafusal fibers are going to be the ones that are doing the contracting mostly. These are surrounded by the sarcolemmal membrane. Each fiber is going to consist of several hundred to 1,000 myofibrils. Each myofibril is going to have about 1,500 myosin filaments and 300 actin filaments. The filaments are going to be inside of the matrix of the muscle cell, which is known as the sarcoplasm. Inside of that is the sarcoplasmic reticulum, which contains the calcium ions. The T system is what allows for the conduction of the electrical signal of the impulse from the neuromuscular junction through the muscle fiber. So the T system is going to be the T tubules, which is going to be continuous with the sarcolemma, runs transverse to the myofibrils, branching among them. The striations are going to be formed by the actin and myosin. So our I band is going to contain only actin filaments. A band is going to contain myosin and actin filaments. The H zone is going to contain lighter bands, and the Z disc is going to contain darker bands. Right. The area between the two Z discs or Z lines is what is known as the sarcomere, and this is the contractile unit or the functional unit of the skeletal muscle fiber. So the myosin filament is going to be the heavier of the two. Okay, we're going to have a molecular weight of about 460,000, which is pretty heavy as far as a protein is concerned. One molecule is going to contain 6 polypeptide chains, 2 heavy chains, and 4 light chains. The actin filament is going to actually be a complex of 3 different components. We have the actin itself, we have the tropomyosin and troponin. Okay. There's a hexagonal arrangement of actin and myosin filaments. So we see one myosin actually surrounded by 6 actins bordering it. The mechanisms of contraction, we're going to have excitation contraction coupling, What that means is that we have skeletal muscle fibers innervated by alpha motor neurons. These are going to receive signals at the neuromuscular junction, which is going to contact the motor end plate on the muscle. The neurotransmitter we use here is acetylcholine, and this is synthesized in the cytoplasm of the terminal end plate. Across the synaptic cleft, acetylcholine is degraded by an enzyme known as acetylcholinesterase. The action here, right, when the action potential spreads, the voltage-gated calcium channels open. Large quantities of calcium will diffuse to the interior. The calcium ions are going to have a direct contact and influence with the acetylcholine vesicles. Those vesicles are going to attach to the membrane at the end of the axon and diffuse out into the synaptic cleft. Acetylcholine is going to move into the synapse by exocytosis. It's then diffusing across the synaptic cleft and attaching to the acetylcholine receptors on the motor end plate, which are known as gated ion channels. When those gated ion channels open, they will allow for sodium ions to move inside. This will create a local end plate potential, which will initiate an action potential on the surface of the muscle. Action potential of the skeletal muscle specifically, we have a resting membrane potential of around negative 90 millivolts or so. Duration of the action potential is going to be 1 to 5 milliseconds, which is going to be 5 times as long as it is in large velocity of conduction, right? The velocity of conduction for our action potential is about 3 to 5 meters per second, which is going to be because of myelination. We see depolarization because of the influx of sodium and the repolarization because of potassium efflux. Action potentials are going to move along our transverse tubules. Once we have initiated that at the motor end plate, transverse tubules will lead to excitation of the ion channels on the sarcoplasmic reticulum, which will release calcium ions into the muscle fiber and muscle cell, leading to contraction. The overall process here is excitation-contraction coupling. Our calcium is going to initiate contraction by binding to troponin on top of the actin molecules. Once we bind to the troponin, we're going to have a conformational change or a physical movement of those fibers, which means that our tropomyosin is going to move away from the binding sites for myosin on the actin chain. Once that moves, or once tropomyosin moves away from the binding sites on the actin, our myosin heads now have a place to attach. So opening the active site allows for attachment. As soon as that attachment occurs, we're going to change the intermolecular forces between the head and the arm. The head is going to tilt towards the arm and the actin filament is going to be moved along it. After that happens, we have to remove it, right? So we're going to break away from the attachment site by resynthesizing ATP here. The head is going to return to its normal direction. The head is then going to use that ATP to cleave off energy for that third phosphate to allow the head to recock into a new position, and then will combine itself with a new active site and will continue to pull that actin filament in. This is known as the sliding filament model. So here's our sequence of events. First, we have to have electrical signal change. So we have a discharge at the motor neuron. At the motor neuron, we will release acetylcholine as the neurotransmitter. It will move across the synaptic cleft and bind to the nicotinic acetylcholine receptors on the muscle surface. That will open the ion channels for sodium and potassium. This will create an end plate potential, which will generate an action potential in the muscle fibers. That depolarization and action potential will move along the T-tubule system. As we move along the T-tubule system, we will start to release calcium from the terminal cisternae of the sarcoplasmic reticulum. That calcium will diffuse around the muscle fiber, binding to the troponin protein on top of actin. This will uncover the myosin binding site by moving tropomyosin away from it. At that time, the myosin head will be able to bind to the actin, and we will pull the thin filament in towards the thick filament. Relaxation is going to be much simpler. The calcium is simply pumped out of the muscle cell back into the sarcoplasmic reticulum. We will release the calcium from the troponin and move the tropomyosin back in front of the actin binding sites. And we'll have cessation of interaction between the two proteins. All right, manifestation of skeletal muscle activity. We see electrical, chemical, and mechanical. Electrical is going to be the process of the electrical signal change. So polarization, depolarization, and repolarization. We measure this by using what is known as an EMG or an electromyography reading. We do surface EMG by using metal discs. We can do a deep EMG by using needle electrodes put into a single muscle. We see chemical changes. We see 3 pH changes. See a decrease in pH when dephosphorylation of ATP occurs. We see formation of basic creatine after the creatine phosphate system, and we see accumulation of lactic acid. For mechanical, this is known as the myographic curve, right? And this is the physical change. This is the actual physical movement of the muscle itself. All right, so types of contractions. We have 2 types of contractions, isometric and isotonic. Isometric contraction is going to be pushing force against something without changing the length of the muscle. Isotonic is going to be keeping the same tone in the muscle, but we are changing the length, so we're able to move against a load. So moving on to different muscle type here. Some mechanisms of excitation and contraction of smooth muscle. It's regulated by both our myogenic pacemakers and also the humoral hormone responses. So we've got catecholamines, estrogens, oxytocin, everything that's under involuntary control. Neuromuscular junctions at the smooth muscle are going to be slightly different. Right? We have a secretion of transmitter substance into the interstitial fluid and diffusing that into the muscle cells. So our terminal axons actually have what are known as varicosities containing neurotransmitter. All right. Most smooth muscle cells are going to be innervated by both parasympathetic and sympathetic nerves. All right, next is going to be the summation of contraction rule. All right. This is known as the all or none rule or all or none law. All right. This is going to be where we have repeated stimulation, and that is going to be the summation of contraction. The muscle as a whole does not have a refractory period. Okay, so that means that we can have continuous stimulation of the muscle. And if we have continuous stimulation of the muscle, it will reach what we call a tetanic contraction. There can be complete tetanus where there's absolutely no change in the force output, and an incomplete tetanic contraction where there is a slight undulation of force output. Mainly, what's going to happen as far as force production in the skeletal muscle is going to be an increase in muscle response due to an increase in discharge. So the frequency of discharge is going to increase as far as an individual motor nerve is concerned. Stimulation frequency for complete tetanus is going to be summation of contractions, right? If we're looking at something like a cold-blooded frog, it's going to be about 20 hertz. Mammals, humans, 50 to 100 hertz as far as the electrical potential. At the maximal contraction, we have the recruitment of all the motor units that are there. More motor units are going to be activated with an increasing voluntary effort. So looking at receptors for skeletal muscle are comprised of what we know as muscle spindles. These are about 2 to 10 muscle fibers put together. These are going to be the extrafusal fibers plus their endings. It's innervated, right? We have alpha motor neurons, which are going to contact the extrafusal fibers, and we have gamma motor neurons, which are contacting what we know as intrafusal fibers. Motor units are going to be the functional portion. Okay, so a motor unit is going to be one motor neuron in all of the muscle fibers that motor neuron innervates. So this can be anywhere from 5 muscle fibers for a motor neuron to 1,000 muscle fibers for a motor neuron. It's going to be dependent highly on where you are, what type of muscle you're in, and what that muscle's function is. Skeletal muscle blood flow, again, during exercise, we're going to get about a 10-fold increase. So we can get an opening of 2,000 to 2,500 calories per millimeter squared area. At rest, right, we're opening only about 100 per millimeter squared. So again, there's that 10, 15 time increase for there. So blood flow of the resting skeletal muscle could be 2 to 4 milliliters, all right, per 100 grams of tissue. We're going to increase that a ton during contraction, so we can get it up to anywhere to around 100 milliliters per 100 grams of tissue. All right, physical manifestations of skeletal muscle. The strength or force is the maximal weight held up against gravity. Cold-blooded animals, you can see 3 to 4 kilograms per centimeter squared. In humans, it's much more variable, 3 to 10 kilograms per centimeter squared. So strength is one thing, work is another. Work is going to be positive when we're doing isotonic contraction or when the actual length of the muscle is changing. It's negative when the muscle is being lowered against the weight, or we're seeing a eccentric contraction, and it's static when we have an isometric contraction or no change in length. Overall mechanical efficiency of a skeletal muscle is going to be the work done divided by the total energy consumption. It's going to be 0 during isometric contraction, up to 35% during isotonic contraction. We're going to have heat production, of course, at all times. At rest, skeletal muscle is going to be producing heat. All right. The initial heat is going to be the activation heat. This is going to be whether we're having contraction or not. Shortening heat is only going to happen during isotonic contraction. Recovery heat is the muscle heat that's produced after the exercise is over. So for the restoration of the muscle's pre-contractile state, we are releasing heat as well during that time. All right, finally, energy sources. We're using ATP, of course. So we're using ATP for the transport of calcium and also for the myosin head recocking every time that it dissociates from action. We also need resynthesis of ATP from the phosphocreatine and resynthesis of phosphocreatine from glycogen. If necessary, we also get energy from free fatty acids, amino acids, and acetoacetic acid. Free fatty acids are going to be the major substrate for muscles at rest. All right, muscular fatigue. This is going to happen because of prolonged contraction or prolonged strength of contraction and because of depletion of glycogen. So when you exhaust the metabolic stores and you increase the accumulation of metabolites like lactic acid, you'll see an overall degradation or decline in the amount of force and efficiency that the muscle can contract with. We see central fatigue from synapses in the brain itself of the central nervous system, and this has a protective effect. For contraction, for long-lasting contraction, if we see calcium input into the reticulum, it's going to be inhibited. So that means the relaxation does not occur. ATP is going to be necessary for the transport of calcium back into the sarcoplasmic reticulum. So a lack of ATP can cause a prolonged contraction. This is one of the main reasons that we see rigor mortis after death. Okay. So after death, there's an incomplete depletion of calcium because there's no more ATP. So if there's no more ATP, that means that we're going to have a accumulation of lactic acid, a decrease in pH, and the myosin heads are going to attach to the actin in a fixed way. Okay, let's see. What's next? So the time frame for rigor mortis, again, we have the Neiston law. This is going to be about 1 to 2 hours after death. We start to see this in the heart. Skeletal musculature, this starts to happen for about 3 to 6 hours after death. You see it in the diaphragm, the head, the neck, trunk, arms, hands, and legs, in that order, just about. Relaxation is going to take a good while, so it's going to take about anywhere from 2 to 4 days or so after death for this relaxation to occur. This is because of proteolytic enzymes that enter into there and start to degrade those attachments. All right. So that was exercise and skeletal muscle. Please like and subscribe to the channel. Twisted Science. Also, the Patreon, patreon.com/Twisted Science for more content. Thank you all for watching our exercise physiology lecture, and I will see you for our next video. Peace out.